On 4.2 problems, there's not a lot to say for 1 and 2. Know your strong acids and bases, and then the molarities become the molarities of H plus and OH minus. You might also have to convert to moles and then put it over liters. I know they wrote this a bit odd, but if you see that this is going to give you moles, that answer then exists on the top of the fraction and is divided by the liters, giving you molarity. On number 3, solving for x is not really what we're going to do with the icebox, but we do need to set it up. We know the value of x without the icebox because we know the pH. And so the H plus molarity will be the inverse log of the negative pH. That will give us molarity. Make sure you know how to take inverse log on your calculator, and don't arrive with a calculator you don't understand, right? So here's the molarity, and that is x, isn't it? So how do we find Ka? Well, we know that this is x and that is x, so we end up with the value squared over, well, let's disregard the minus x, over 0.12, and that gives us Ka. For number 4, the trick is realizing that what we've got here is an N with 3 covalent bonds and 2 H's on one side. That leaves that unprotected valence lone pair out in the open, which is good for bonding to a third H. And so that's what's happening. And don't forget to make sure that you realize it's coming off of water effectively. In effect, that leaves OH minus over here, which is how we can have something to calculate pH with eventually. Set up an icebox. One of these creates one of those and one of those. This doesn't have a molarity, so that column is blank. Products over reactants to the power of the number in front. This number is too small, forget it. Solve for x, that is the value of OH minus, and then our standard math to find pH. Number 5 doesn't really have a special trick. They tell you it's an acid. That's supposed to be the acidic H in case you were wondering. And we set it up in an ice box. We can disregard that X because the Ka is too small compared to this molarity. And we find the pH. On number 6, the only trick is realize that you're putting in effectively the anion of a weak acid. You're putting in potassium cyanide, and that's cyanide and potassium on it, but we know potassium's a super soluble, so it all comes off. So this is the molarity of the cyanide ion here. What would a cyanide ion do in water that affects pH? Well, hydrogen cyanide is not a strong acid. You have to know your strong acid and base lists. So forming this is possible. This reaction actually can happen. And we can set up an ice box and then disregard X there, and it's pretty standard. On 7, the trick is realizing what you've got here. These are going to split up when they hit the water because NH4 is a super soluble, that's ammonium. And then what could happen? Well, this could take an H, I guess, except that you're trying to form HCl in water, and that's a strong acid, which means it's impossible, so no, you won't. When this gets into water, this is NH4, and it's really key that you see the 4. This could be an acid. I mean, it's not a strong acid, but it could act as an acid. There's no such thing as NH5, and if you go to the Lewis diagram, I think you'll see that. So it could give up an H, and you could have this reaction here, except they give you Kb, so we're going to need to do Kw minus, divided by Kb to get Ka, and after that, it's pretty standard stuff. 8a has no real tricks here. I'll just point out, don't divide molarity by liters to try to get molarity. They already handed us molarity. If this says 3 liters or something, just disregard it. I already have the molarity. The molarity is the point for my icebox. They even say it's an acid, so this could be our reaction. One of these creates one of those and one of those, so that we get these values, products over reactants to the power of the number in front, except the Ka is so small, 10 to the minus 8, pretty small, that I'm going to cross out this, solve for X, that's the H plus, and negative log of that is pH. On B, we add strong acid to it, so we know that this moles is the moles of the H plus, which divided by the 1 liters from the top gives me a starting molarity of H plus. This acid, again, exists in an unchanged amount. Remember, we said let's just forget the minus X part, so let's leave this back essentially unchanged, because that's what we said in part A. And then we get equilibrium values, which we can put into the Ka expression. Again, that Ka is so small that let's just cross out plus X and minus X. We solve for X. Now, to be picky, the H plus concentration that can get me the pH is the starting value plus the X value, but the X value is so small that there's no effective point in adding it in. So I ended up with the same value, and that was a typo. Oops on them. So when we take negative log of the H plus concentration, ignoring that because there's no point, we get pH of 3, which here they point out the strong acid determines the pH, by which they mean if we could have just skipped this whole icebox thing and said, you know what, the effect of this on the pH compared to that is going to be immaterial. This is going to contribute such a small amount compared to that that it's going to be what, a 0.05% or something. Anyway, it's going to be small. I mean, small. So I'm just going to say forget it. On a logarithmic scale like pH, I'm going to say forget it. And the pH is effectively the negative log of that number without all this extra math, because the pH is still negative log of 0.001. In part C, adding the anion here attached to a super soluble, so let's just cross that out, really does affect the pH. We know that the K's all come off. This is the moles of the anion. It's in 1 liter, so that becomes the molarity of the anion. And adding in the anion by Le Chatelier's principle will push this to an appreciable amount back left, which reduces the H plus. If this thing's going to travel back left, then this has got to get used up, and we will not get the same answer as if we ignore the icebox. Let's go through it. One of these creates one of those and one of those, and we end up with these equilibrium amounts. We can cross out plus x and minus x. When we solve for x, we get this, and that is the H plus molarity, negative log, etc., and we do not get the same value. And this pH value is higher, which means it's more basic, which means there is less H plus in the solution, which is what I said before. This is going to push left, and this is going to use this up. Does that make this solution more acidic or more basic? It used up the acidic character. It makes it more basic. Does that push the pH up or down? It pushes it up. Also, we could solve it with the Henderson-Hasselbalch equation because we know Ka, and if we regard plus x and minus x, you could just put it in here and get the same answer.